Transition metals. Transition metals are otherwise known as D-block elements. Most of the transition metals have moderate to high densities, good electrical conductivity, high melting points, and moderate to extreme hardness. Their similarities are related to their similar electron configurations. Despite their similarities, each element is unique, and as a category of metals, they exhibit a wide variety of chemical behaviors. The ground state electron configuration for the first two rows of transition elements is Ns2, N-1D. In third and fourth rows, it is Ns2, N-2, F14, N-1D. The energy of the Ns and N-1D are very close, and as a result, many exceptions occur among these elements. They may lose electrons from these close energy sublevels and form multiple cations. Across the period or row of the D block, the number of electrons in the outermost energy level remains constant. For every proton added, an electron is also added, but it goes to the N-1 energy level. They experience a roughly constant effective nuclear charge, keeping the atomic radius approximately constant. Down the group, a small but expected increase within the first and second rows, while there is not much difference in the size of the elements from second row and third row. Ionization energy values of transition metals follow the same trend as the main group elements, increasing across the row. Down the group, the third row has the higher ionization energy. Transition metals often exhibit a variety of oxidation states. The highest oxidation state for a transition metal is +8 for manganese. Transition elements could lose the Ns and N-1D electrons to form multiple oxidation states. They tend to form complex ions containing a central metal ion bound to one or more species called a ligand or a Lewis base. When this complex ion combines with one or more counter ions, the resulting compound is known as a coordination compound. This is very unique for transition elements compared to the main group elements. Such compounds are commonly found in living systems, industry, and even in household products. Extraction of iron. The chief ores of iron are made up of various forms of iron oxides: hematite, magnetite, limonite, siderite, and iron pyrites. The three forms of iron used widely are cast iron, which are 3 to 5% carbon, wrought iron, 0.2 to 0.5% carbon, and steel, 0.1 to 1.5% carbon. They differ in properties due to their carbon and phosphorus content. Cast iron is also known as pig iron. The process of iron extraction from its ore involves the following steps: concentration, calcination, sintering, smelting. In the concentration step, the ore is broken down into pieces of 3 to 5 centimeters in size. Clay, sand, and other surface impurities are removed by washing with water. During calcination, the concentrated ore is heated strongly in a controlled supply of air to 1. Remove moisture and carbon dioxide, and 2. Oxidate arsenic and sulfur if any present, according to the reactions below: the oxidation of sulfur and the oxidation of arsenic. And then 3. Convert any ferrous oxide, FeO, to ferric oxide, Fe2O3, as shown in this 3-step process. The calcination step avoids the formation of ferrous silicate slag during smelting and makes the entire mass porous and easier to reduce. Sintering is necessary if the calcinated ore is powdery. Sintering is a process in which the surface particle is melted to hold the entire mass together without losing its porosity. Smelting is carried out in a blast furnace, which is a tall steel vessel lined with fire bricks. The sintered ore is mixed with limestone and coke, 8:1:4, 8 parts sintered ore, 1 part limestone, 4 parts coke, and is introduced into the blast furnace from the top. Preheated air at 873 Kelvin is passed into the furnace from the bottom. There are different heating zones in the furnace where a variety of chemical reactions, such as combustion, reduction, decomposition, occur during treatment. Here's the top of the blast furnace where the roasted ore, coke, and limestone are added. You can see the preheated air. At the end, we get this molten iron and any slag. In the zone of combustion, the preheated air comes in contact with the coke and the combustion of the coke takes place. This reaction is a highly exothermic one, causing the temperature to rise to about 2100 Kelvin according to the reaction below. So the coke reacts with the oxygen, producing carbon dioxide and a lot of heat. This carbon dioxide rises up, reducing different layers of coke to carbon monoxide according to this reaction shown. In the zone of reduction, the carbon monoxide acts as a reducing agent. This reduces the iron oxide to iron. The temperature varies from 800 to 1575 Kelvin in this zone and is considered as the top zone in the furnace. A variety of reactions takes place here as listed below. So you can see the reaction between Fe2O3 and carbon monoxide to produce iron, molten iron, or to produce iron oxide. Fe3O4 can react with the carbon monoxide to produce FeO and carbon dioxide. FeO can react with coke to produce iron and carbon monoxide, and several other reactions as well. In the zone of slag formation, the limestone, which acts as a flux, decomposes at a temperature of 1073 Kelvin. This is the middle zone of the furnace. The quicklime reacts with sand impurities, SiO2, to form a slag of calcium silicate according to the reactions below. So the limestone decomposes. We get this calcium oxide, quicklime, which reacts with the sand impurities to form a slag of calcium silicate. The molten slag, being lighter than iron, floats on the top. Both slag and molten iron are drawn off. The molten iron tapped off is solidified into blocks known as pig iron or cast iron. This form of iron contains about 3 to 5% carbon and varying amounts of elements, manganese, silicon, sulfur, and phosphorus. These impurities makes the iron hard and brittle. Cast iron cannot be forged or welded by hammering. When melted, cast iron solidifies, expanding slightly. It is used extensively in casting toys, radiators, pipes, and agricultural implements. Wrought iron, a comparatively pure form of iron, is produced when cast iron is refined by oxidizing with hematite, Fe2O3, according to the reaction below. So, Fe2O3 with this carbon producing this more pure form of iron. Carbon monoxide thus escapes, while manganese oxide present combines with SiO2 to form slag according to this reaction. Wrought iron, thus formed, contains 0.2 to 0.5% carbon and traces of phosphorus and silicon. This form of iron is ductile, soft, and malleable. The slag impurities makes it tough and resistant to corrosion. Wrought iron is used to make magnets in cranes and dynamos. It is also used to make chains, anchors, bolts, nails, railway couplings, and ornamental gates. Steel. Pure iron by itself is not very useful, but the addition of metals and carbon converts it into steel. Various steels have different carbon content varying from 0.1 to 1.5%. Increasing carbon content in steel increases its tensile strength and decreases its ductility. 3 common methods are in use for the production of steel: the Bessemer process, the open hearth process, and the electric furnace process. Steel has a melting point between 1573 and 1673 Kelvin. It is very hard and malleable. Steel can be welded, tempered, and has high tensile strength. It is used for making cutting tools, axles, rails, measuring instruments, engine parts, and steel alloys. Copper occurs as native copperous iron 2 sulfate as well as in combined state. The principal ores of copper are copper glance, Cu2s, copper pyrites, CuFeS2, cuprite, Cu2O, and malachite. Copper is mainly extracted from copper pyrites, which you can see shown here. The powdered ore is concentrated by the froth flotation process, then roasted in a limited supply of air, so you can see that oxygen there, in a reverberatory furnace. This heating will convert iron into iron oxide. Arsenic and antimony present as impurities are removed as volatile oxides according to the reactions below. The roasted ore is then smelted by mixing it with sand and heating strongly in a blast furnace. Most of the iron sulfide is converted to iron oxide, and it forms slag with silica and removed according to the reactions below. Ultimately, you can see this slag formed with SiO3. Cuprous sulfide or copper 1 sulfide along with some ferrous sulfide, FeS, left after smelting is called matte. It is removed as the lower layer from the blast furnace. The copper must go through Bessemerization when it is recovered from the molten matte using a Bessemer converter. The matte is transferred into a Bessemer converter and a blast of air and sand is blown through the molten matte. This reduces copper 1 sulfide to copper. Any iron oxide remaining will be converted to slag and removed. The reactions below describe the changes that take place during Bessemerization. You can ultimately see the production of copper and this iron-containing slag. After Bessemerization, the copper obtained is 99% pure and is used for many purposes. The molten copper is poured off and any SO2 will escape up on cooling, forming blisters on the surface. This is known as blister copper. Blister copper is refined by poling process. The blister copper is melted in the hearth of a reverberatory furnace and hot air is passed through it. Any impurities present are removed either as volatile oxides or as slag, which is skimmed off. Some copper 1 oxide formed is reduced to copper by stirring with poles of green wood, which give reducing gases. Bessemerized copper is further refined electrolytically to obtain 99.99% purity by using a solution of copper sulfate as the electrolyte. An anode sludge or mud containing silver and gold settles down. The crude copper is used as the anode and a thin sheet of pure copper as the cathode. The pure copper is deposited at the cathode according to the reaction below, where we get solid copper building up at the cathode and the anode having these copper ions. Uses of copper. It is extensively used for making electric cables and other electric appliances. It is used for making utensils, containers, kettles, coins, calorimeters, and similar items. It is used for electroplating and electrotyping. It is used for making a large number of alloys. Copper is added with gold and silver to make ornaments and coins.